The Metered Agentic Economy, AI Compute, Tokens, and Machine Commerce. Subtitle: How AI Compute, Protocol Tokens, and Stablecoin Settlement are transforming machine capability into a metered global infrastructure economy. Section 1, Introduction, the End of the Attention Economy. For nearly 30 years, the internet economy revolved around one dominant business model: attention extraction. The logic was simple. Humans used digital services. Platforms captured attention. Advertising monetized eyeballs. The more time users spent scrolling, clicking, watching, liking, or reacting, the more valuable the platform became. The modern internet was built around manipulating human behavior. But agentic AI changes the consumer itself. Machines are now becoming the primary consumers of compute, inference, APIs, storage, bandwidth, and digital services. And machines do not behave like humans. Machines do not click advertisements. Machines do not respond to emotional persuasion. Machines do not impulse buy because of color psychology or celebrity endorsements. Agents optimize for utility, latency, reliability, efficiency, and cost. This changes the economic architecture of the internet. The digital economy begins shifting away from attention extraction and toward metered infrastructure. That distinction is critical. In the old internet, human attention was the scarce commodity. In the emerging agentic economy, compute becomes the scarce commodity. This changes the monetization layer entirely. Instead of monetizing eyeballs, engagement, and emotional manipulation, the emerging AI economy monetizes compute cycles, inference requests, bandwidth, robotic labor, energy consumption, and machine coordination. The internet begins behaving less like a media ecosystem and more like a global utility grid. That is why the infrastructure layer suddenly matters again. AI is not lightweight software in the traditional sense. It is industrial infrastructure. Behind every inference request sits electricity, GPUs, cooling systems, networking equipment, semiconductor supply chains, data centers, maintenance crews, and increasingly, national-scale energy systems. Every query has a real-world marginal cost. This is why AI naturally drifts toward metering. The strongest analogy is not social media. It is electricity, or cloud computing, or telecom bandwidth. The world is moving toward a metered, tokenized, agent-native economy where compute becomes the new oil, protocol tokens become the plumbing, and stablecoins become the lubricant. This framework explains why crypto, AI, stablecoins, decentralized infrastructure, and machine commerce are beginning to converge into the same economic stack. Public blockchains increasingly function as programmable coordination systems for global machine infrastructure. Stablecoins become machine-native payment rails. Protocol tokens become infrastructure coordination mechanisms, and AI compute itself begins evolving into a globally traded utility. This evolution is already visible. Decentralized compute networks such as Akash, Render, IONET, Bitensor, and Venice are already experimenting with tokenized GPU markets, metered inference systems, staking mechanisms, and globally distributed compute coordination. At the same time, hyperscalers such as Microsoft, Amazon, Google, and Meta are collectively spending hundreds of billions of dollars building AI infrastructure at industrial scale. This is not merely a software cycle. It is the construction of a new utility layer for civilization. And like all utilities, it requires pricing systems, ownership structures, allocation mechanisms, and settlement rails. That is where tokenization enters the picture. The most important insight is this: crypto is not merely becoming internet money. Crypto is becoming the coordination and settlement layer for machine-to-machine commerce. That changes the role of tokens entirely. In the speculative era of crypto, tokens were often treated as little more than volatile digital assets. But in the agentic economy, tokens increasingly function as programmable ownership rights, staking instruments, infrastructure coordination systems, allocation primitives, and machine settlement mechanisms. Stablecoins solve pricing, accounting, and payment stability. But protocol tokens solve governance, distributed ownership, incentive alignment, and infrastructure coordination. That distinction becomes increasingly important as AI infrastructure expands globally. Without native protocol layers, AI infrastructure remains centralized. With tokenization, infrastructure can become globally financed, globally coordinated, and globally participated in. This matters because AI compute naturally prefers aggregation across continents. Compute seeks cheap energy, cheap cooling, low-cost manufacturing, resilient routing, and geographic redundancy. A decentralized protocol can coordinate all of this globally. And once machine capability becomes measurable, rentable, reservable, and programmable, a much larger transformation begins to emerge. AI compute starts behaving like infrastructure real estate. Inference capacity becomes rentable, GPU allocation becomes leasable, machine capability becomes yield-bearing, and eventually synthetic labor itself becomes tokenizable. The world is beginning to build digital toll booths around machine capability. That may sound abstract today, but the implications are enormous. Because once AI compute, robotic labor, and machine infrastructure become tokenized, metered, and globally tradable, the economy itself begins transforming into something fundamentally new: a metered machine civilization. Section 2. Compute becomes the new commodity. Throughout modern industrial history, civilizations have been shaped by the control of foundational commodities. Coal powered the Industrial Revolution. Oil powered the automotive age and the petrodollar system. Electricity powered the 20th century. Semiconductors powered the digital age. Now a new commodity is emerging at the center of the global economy: AI compute. More specifically, compute cycles, inference capacity, GPU access, networking throughput, and machine coordination. The most important distinction is between training and inference. Training is expensive but episodic. A frontier model may require enormous capital expenditure during development: massive GPU clusters, months of compute time, huge energy consumption, and specialized engineering teams. But once training finishes, the real long-term economic layer begins: inference. Inference is perpetual. Every AI interaction requires ongoing compute, answering queries, generating media, coordinating agents, processing robotic inputs, optimizing logistics, executing workflows, and eventually running machine economies autonomously. Training creates the machine. Inference keeps the machine alive. That distinction matters enormously because recurring inference demand transforms AI from a software product into a metered utility. This is where the economics begin to resemble electricity grids, telecom bandwidth, cloud infrastructure, or industrial fuel markets. And the numbers already reveal the scale of the transformation. Global data center electricity consumption reached roughly 415 terawatt hours in 2024, approximately 1.5% of total global electricity demand. By 2030, projections suggest this figure could approach 945 terawatt hours, with AI infrastructure responsible for much of the increase. In the United States alone, data center electricity demand may rise to between 6.7% and 12% of total national electricity consumption by 2028. These are not software numbers, these are industrial numbers, grid numbers, nation-scale infrastructure numbers. This is why many of the world's largest technology firms are now behaving less like software companies and more like utility operators. Microsoft, Amazon, Google, and Meta are collectively projected to spend between $630 and $710 billion on infrastructure expansion during 2026 alone. Much of this spending targets GPU procurement, data center construction, electrical infrastructure, networking, and energy access. Meanwhile, OpenAI itself is projected to lose billions annually despite explosive growth. Why? Because AI inference is physically expensive. Every query consumes electricity, GPU occupancy, cooling, memory bandwidth, and infrastructure wear. The market is slowly realizing something important. AI is constrained by physics, not merely software. This introduces a fundamental economic reality. AI services cannot infinitely scale under traditional internet monetization models. The old internet could subsidize services using advertising, engagement manipulation, attention capture, and behavioral targeting. But agentic systems fundamentally change the consumer profile. Machines do not generate advertising value. An autonomous trading agent does not care about banner ads, emotional persuasion, celebrity influence, or social media manipulation. It optimizes purely for utility, speed, reliability, and cost efficiency. That means AI infrastructure naturally drifts toward metering, utility pricing, reservation systems, spot markets, and machine-native settlement rails. The strongest analogy is not Facebook. It is AWS, or electricity, or telecom infrastructure. This is where Jevons paradox enters the picture. Historically, whenever efficiency improves, total consumption rises rather than falls. Cheaper electricity increased electricity consumption. Cheaper bandwidth increased internet traffic. Cheaper storage increased data generation. And cheaper compute is already increasing AI demand dramatically. Efficiency improvements such as quantization, optimized architectures, custom silicon, and inference acceleration reduce the cost per operation. But they simultaneously expand the number of possible use cases. Lower costs allow more agents, more automation, more robotics, more inference loops, and more machine participation. This is why AI demand may continue compounding for decades, not because compute remains inefficient, but because cheaper compute expands civilization's dependence on machine intelligence. This changes the strategic importance of compute itself. Oil-powered industrial civilization. Compute may power machine civilization. And unlike oil, compute possesses several unique characteristics: perfectly meterable, digitally routable, globally allocatable, infinitely composable, and programmable at machine speed. This makes compute particularly suitable for tokenization, dynamic pricing, programmable ownership, and automated settlement systems. Which brings us to the next major transition, the rise of the digital toll booth economy. Section 3, the digital toll booth. As AI infrastructure expands, a new economic model begins to emerge around it. The digital toll booth. Every interaction with machine intelligence increasingly becomes measurable, billable, metered, and economically routable. This is not accidental. It is the natural consequence of turning intelligence into infrastructure. In the traditional internet economy, monetization was often indirect. Users received free services while platforms monetized: attention, data, behavioral profiling, and advertising exposure. But AI changes the economics completely. Inference is not free. Every AI output consumes compute cycles, GPU time, electricity, bandwidth, memory, and physical infrastructure resources. That means the system must eventually answer a simple question: who pays for the machine? The answer increasingly appears to be usage-based metering. This is why the old phone booth analogy becomes surprisingly powerful. You insert value into the system. The machine responds. When your balance runs out, access stops. The economics are no longer advertising first. They become utility first. This is already visible across both centralized and decentralized AI systems. Hyperscalers such as Microsoft Azure, AWS, Google Cloud, and OpenAI APIs already monetize AI primarily through pay-as-you-go, PAYG inference pricing, enterprise reservations, token usage billing, and compute allocation systems. At the same time, decentralized protocols such as Akash, Render, IO.net, and Venice are experimenting with tokenized GPU marketplaces, on-chain compute metering, staking-based access rights, and globally distributed compute leasing. These systems increasingly resemble electricity markets for intelligence. And this is where stablecoins become extremely important. Machines require stable accounting, predictable budgeting, sub-cent precision, low-friction settlement, and globally routable liquidity. Volatile assets are poor settlement instruments for autonomous agents. A machine cannot reliably budget future inference costs using assets that fluctuate wildly in value. Stablecoins solve this problem elegantly. USDC, USDT, and similar dollar-backed instruments allow machine-native pricing, programmable payments, automated accounting, and low-volatility machine commerce. This is why stablecoins increasingly resemble machine money, not because machines ideologically prefer dollars, but because stable units reduce operational uncertainty, improve budgeting, simplify routing, and reduce settlement friction. This creates a powerful architectural stack. Compute becomes the resource. Stablecoins become the settlement layer. Protocol tokens become the coordination layer. Together, they form the economic foundation for machine-to-machine commerce. This is where one of the internet's oldest business models begins to weaken dramatically: advertising. The reason is simple. Machines do not click ads. An autonomous agent searching for compute, transportation, logistics, or procurement does not care about emotional persuasion, social signaling, influencer marketing, or banner placement. It optimizes strictly for utility, latency, reliability, and cost. This changes the monetization architecture of the digital world. The internet gradually shifts away from attention extraction and toward metered infrastructure. That distinction may ultimately define the next era of the global economy. The implications become even larger once agents begin transacting continuously with one another. Machine-to-machine commerce creates perpetual settlement flows, autonomous procurement systems, programmable service markets, and globally routable infrastructure demand. An AI agent may eventually purchase compute from one network, storage from another, robotic labor from another, and bandwidth from a fourth, all autonomously. At that point, crypto stops being merely speculative finance. It becomes the settlement rail for machine civilization. This is one reason public blockchains are increasingly important. Blockchains allow programmable payments, permissionless access, global settlement, composable infrastructure, and automated coordination. They become economic operating systems for machine activity. And unlike traditional financial rails, they can operate continuously, globally, and programmatically at machine speed. This creates the conditions for a truly global utility market around intelligence itself. A world where compute is rented, inference is leased, robotic labor is allocated, machine services are auctioned, and infrastructure is dynamically priced in real time. In effect, intelligence itself becomes a metered utility layer. And once intelligence becomes metered, another transformation begins to emerge: ownership. This content is brought to you by Bobby Giggs. Promote your brand here and reach a wide audience across platforms like YouTube, Instagram, and Facebook. Follow the links in the description to get started. Section 4. Protocol tokens, the coordination layer. Once intelligence becomes metered, the next question naturally emerges: who owns the machine? This is where the distinction between stablecoins and protocol tokens becomes critically important. Stablecoins are excellent payment systems. They solve pricing stability, accounting, settlement, liquidity routing, and machine-native commerce. But stablecoins alone cannot coordinate decentralized infrastructure. They cannot easily solve distributed ownership, governance, staking, capital formation, long-term incentive alignment, or infrastructure bootstrapping. That is the role of protocol tokens. This distinction is often misunderstood because many people still view crypto primarily through the lens of speculation. But in decentralized infrastructure systems, native tokens increasingly function as coordination mechanisms, ownership primitives, staking bonds, and programmable infrastructure rights. The token becomes the ownership ledger, the incentive layer, the fundraising mechanism, the governance system, and the allocation engine. This is why native tokens continue to matter even when stablecoins dominate payments. Stablecoins solve payment stability. Protocol tokens solve infrastructure coordination. That distinction may ultimately define the architecture of decentralized AI systems. To understand why, consider the alternative. A centralized hyperscaler, such as Amazon, Microsoft, Google, or OpenAI, does not necessarily require a native token. Why? Because centralized firms already possess corporate governance, internal balance sheets, centralized ownership, operational hierarchy, legal enforcement structures, and concentrated capital pools. They can raise debt, issue equity, build data centers, and internally manage infrastructure allocation. But decentralized AI infrastructure is fundamentally different. It must coordinate globally distributed hardware, anonymous participants, independent GPU owners, cross-border energy sources, and decentralized capital formation. That coordination problem is precisely what protocol tokens solve. The token allows global participation, distributed ownership, staking, yield sharing, and incentive alignment across thousands of independent actors. This is where decentralized infrastructure begins resembling a globally coordinated utility cooperative, or perhaps more accurately, a decentralized infrastructure REIT for machine capability. The implications are enormous. A participant in Nigeria, India, Brazil, Kenya, Indonesia, or energy-rich regions with low infrastructure costs may contribute GPUs, electricity, cooling capacity, robotics, storage, or bandwidth in exchange for protocol yield, staking rewards, infrastructure ownership exposure, and participation in machine commerce. Without tokenization, these participants merely become customers. With tokenization, they become infrastructure owners. That changes the scaling dynamics entirely. This is one reason decentralized infrastructure can potentially achieve lower operating costs than centralized hyperscalers. A hyperscaler must finance infrastructure internally, build centralized data centers, absorb geopolitical concentration risk, and manage capacity centrally. A decentralized protocol can aggregate idle GPUs, regional energy asymmetries, sovereign compute clusters, home hardware, and globally distributed infrastructure through token incentives alone. This creates geographic redundancy, energy optimization, resilience, and capital efficiency, and increasingly geopolitical resilience. Recent global conflicts have demonstrated how vulnerable centralized choke points can become. Concentrated infrastructure can be sanctioned, disrupted, politically weaponized, or physically targeted. Distributed machine infrastructure is inherently more difficult to censor, control, disrupt, or eliminate. This may eventually make decentralized compute strategically important, not merely economically efficient, and this is where staking mechanics become extremely powerful. Many participants may not wish to actively manage routing, leasing, GPU allocation, or infrastructure optimization. Instead, they may simply stake tokens representing ownership claims on the underlying network. The protocol itself then manages compute allocation, leasing, pricing, reservations, and machine coordination while distributing yield proportionally back to token holders. This begins resembling delegated infrastructure management, very similar to delegated proof-of-stake systems, utility cooperatives, infrastructure trusts, or revenue-sharing industrial networks. The key insight is this: protocol tokens transform machine infrastructure into a globally participatory asset class. This is where the architecture becomes radically different from traditional cloud infrastructure. Under the hyperscaler model, the corporation owns the machines, the corporation captures the yield, and users merely rent access. Under the decentralized protocol model, the network itself can become collectively owned. That ownership layer becomes one of the strongest incentives for global participation, especially across the global south, because participation is no longer limited to consuming infrastructure. People can now own part of the machine economy itself. This may become critically important if the United States wants dollar-based stablecoins to proliferate globally as the settlement layer for AI compute and machine commerce. Why? Because global participants are unlikely to contribute hardware, capital, energy, robotics, or compute resources merely to strengthen the dollar system. They participate because tokenization allows them to own productive infrastructure, receive yield, stake assets, and share in network growth. This creates an important strategic tension. If the U.S. wants stablecoin dominance, AI compute dollar adoption, and machine commerce settlement leadership, then some degree of open wallets, self-custody, DeFi participation, staking access, and programmable financial infrastructure may become strategically necessary. Not necessarily because states ideologically prefer decentralization, but because decentralized participation dramatically improves infrastructure scaling, global capital formation, and network adoption. This creates a new geopolitical balancing act between control and scale. Too much restriction weakens participation, liquidity, network effects, and infrastructure growth. Too much openness weakens state control, regulatory visibility, sanctions enforcement, and monetary gatekeeping. The likely future is not total decentralization, nor total centralization, but a hybrid world where stablecoins handle settlement, protocol tokens coordinate infrastructure, and machine capability becomes globally programmable. And once machine capability becomes programmable, another transformation emerges. Compute itself begins behaving like capital. Section 5. Compute as capital. Once machine capability becomes programmable, a much larger financial transformation begins to emerge. AI compute stops behaving merely like software infrastructure. It begins behaving like capital. More specifically, productive capital, rentable capital, yield-bearing capital, and increasingly, financialized capital. This is one of the most important conceptual shifts in the entire AI economy. Most people still think about AI as applications, chatbots, assistants, or software products. But underneath the interface layer sits something much larger: machine infrastructure capable of generating recurring economic output. That changes the nature of ownership entirely. Historically, productive assets generated value because they could continuously produce something useful. Factories produced goods, power plants produced electricity, telecom towers transmitted bandwidth, real estate generated rent. Now AI infrastructure increasingly generates inference, automation, coordination, robotic labor, optimization, and machine productivity. This is why the compute as infrastructure real estate analogy becomes so powerful. Inference capacity starts behaving like rentable property. GPU allocation becomes reservable, bandwidth becomes leasable, priority access becomes monetizable, and machine capability itself becomes yield-generating infrastructure. This is already partially visible inside cloud reservation systems, GPU marketplaces, staking-based inference protocols, and decentralized compute exchanges. But tokenization dramatically expands the model, because once compute rights become digitally represented, divisible, transferable, and programmable, they can begin functioning like financial assets. This is where AI infrastructure starts merging with capital markets. A token may eventually represent reserved GPU time, future inference capacity, robotic labor rights, network bandwidth allocation, priority queue access, or fractional ownership of machine infrastructure. At that point, machine capability itself becomes tradable. This is where the architecture starts resembling REITs, utility markets, telecom infrastructure, and commodity leasing systems. Only now the underlying commodity is machine intelligence. The implications are enormous. An individual may eventually own inference capacity, robotic fleets, compute reservations, AI labor pools, or globally distributed machine infrastructure, and lease those productive capabilities into open markets. The same way, landlords rent apartments, solar owners sell excess electricity, and telecom operators lease tower access. Future infrastructure owners may lease compute, robotic labor, bandwidth, storage, and machine coordination services. This transforms AI from a software product into a programmable utility economy. And this is precisely why tokenization matters. Without tokenization, compute remains centrally owned infrastructure. With tokenization, compute becomes programmable economic property. That distinction changes everything because programmable ownership enables secondary markets, yield generation, futures markets, reservations, leasing systems, and infrastructure arbitrage. This is where the concept of the financialization of machine capability becomes increasingly literal. The machine itself becomes an income-generating economic primitive. This is already partially visible in projects such as Venice. Venice's VVV architecture hints at an important evolution beyond simple pay-as-you-go inference. Instead of paying per query, users stake tokens representing claims on ongoing inference capacity. This begins looking less like software billing and more like ownership of productive infrastructure. The user is no longer merely consuming AI. The user owns access rights to machine capability itself. That distinction is subtle, but historically significant. Because once ownership rights emerge around productive infrastructure, capital markets naturally follow. Markets begin pricing scarcity, reservations, yield, reliability, throughput, and future production capacity. This creates entirely new categories of financial instruments. Future markets may emerge around inference futures, compute reservations, robotic labor contracts, AI bandwidth markets, and machine capacity derivatives. The architecture begins looking increasingly similar to energy markets, cloud infrastructure markets, and industrial commodity systems. Except now, the commodity is machine capability itself. And unlike traditional commodities, compute possesses unusual characteristics. Compute is globally routable, instantly allocatable, perfectly meterable, digitally divisible, and programmable at machine speed. This makes it uniquely compatible with automated settlement, tokenized ownership, algorithmic leasing, and machine-native commerce. The implications extend far beyond data centers, because once machine capability becomes tokenizable, the same architecture naturally extends into robotics. A robot is ultimately AI, inference, sensors, networking, energy, and physical actuation wrapped into one machine system, which means robotic labor itself eventually becomes allocatable, rentable, leasable, and financially programmable. This is where the emerging world of synthetic labor and automated manpower begins to appear. Section 6, SLAM, Synthetic Labor and Automated Manpower. Once machine capability becomes tokenized, rentable, and globally routable, the next stage of the transformation becomes unavoidable. Labor itself begins evolving into programmable infrastructure. This is where the convergence of AI, robotics, tokenization, and machine commerce starts reshaping the structure of the global economy. A robot is not merely a machine. Economically speaking, a robot is a physical compute endpoint, connected to inference systems, powered by energy, coordinated through software, and capable of generating productive output autonomously. That distinction matters enormously because once robotic labor becomes measurable, allocatable, remotely controllable, and economically billable, robotic labor itself begins behaving like tokenized infrastructure. This is the emergence of synthetic labor and automated manpower, or SLAM. Historically, labor markets depended on human coordination, geographic proximity, payroll systems, immigration flows, and biological limitations. But autonomous machine labor changes the architecture entirely. A robotic worker does not sleep, negotiate wages, emigrate, unionize, or require traditional labor mobility. Instead, machine labor increasingly behaves like bandwidth, electricity, cloud infrastructure, or industrial machinery, meaning it can be leased, routed, allocated, metered, and globally coordinated through software systems. This creates an entirely new category of productive assets. The implications become easier to understand once viewed through familiar infrastructure models. People already understand rental property, Uber fleets, telecom towers, solar feed-in systems, AWS server leasing, and industrial equipment financing. Now extend the same logic into robotic labor. A person may eventually own autonomous taxis, robotic warehouse systems, delivery drones, AI logistics fleets, manufacturing robots, automated agricultural machinery, or distributed machine labor networks. And rather than directly operating them, owners may simply lease productive capacity, delegate routing to protocols, and receive yield from machine output. This begins looking less like employment and more like infrastructure ownership. The same way an apartment generates rent or a solar grid generates electricity revenue, future robotic infrastructure may generate labor yield, automation revenue, fulfillment fees, logistics throughput, and machine service income. This is one reason the Tesla autonomous fleet analogy is so important. People intuitively understand the idea of owning vehicles that autonomously generate revenue. But the concept extends much further. The same architecture can apply to warehouses, ports, accounting systems, fulfillment networks, manufacturing lines, logistics infrastructure, and eventually entire robotic industrial ecosystems. The key enabling mechanism behind all of this is metering. Without metering, there is no pricing, allocation, settlement, or yield generation. The digital toll booth is what transforms machine capability into an economic primitive, and tokenization is what transforms that economic primitive into programmable ownership. This is why tokenization becomes so powerful in the machine economy. Tokens do not merely represent speculative assets. They increasingly represent claims on productive machine infrastructure, claims on machine output, and claims on future automated economic activity. This may ultimately blur the distinction between capital, labor, and infrastructure. Historically, humans supplied labor, while machines amplified productivity. But in a fully agentic economy, machines increasingly become both the worker and the productive capital base simultaneously. This creates entirely new questions around ownership, wealth distribution, capital participation, and economic access. Because whoever owns machine infrastructure increasingly owns productive output, automation capacity, and recurring machine-generated revenue streams. This is why decentralized participation becomes strategically important. Without tokenization and protocol coordination, the future machine economy risks becoming extremely centralized. A handful of hyperscalers could theoretically own the compute, the robotic fleets, the inference infrastructure, and the automation layers. Everyone else merely rents access. But tokenized infrastructure introduces another possibility, distributed machine ownership, where individuals globally can stake into machine infrastructure, participate in robotic economies, receive yield from automated labor, and collectively own portions of the productive machine layer. This is where the convergence between crypto, AI, robotics, and infrastructure finance becomes historically significant because civilization may be entering an era where machine capability itself becomes financially programmable, globally tradable, and continuously monetizable. And once machine capability becomes globally monetizable, another transformation begins emerging at the monetary layer itself, the rise of the AI compute dollar. This content is brought to you by Bobby Gigs. Promote your brand here and reach a wide audience across platforms like YouTube, Instagram, and Facebook. Follow the links in the description to get started. Section 7. The AI compute dollar. For decades, the global monetary system revolved around one foundational commodity: oil. Oil-powered transportation, manufacturing, military logistics, industrial expansion, and global trade. And because oil was primarily priced and settled in dollars, global energy demand reinforced global dollar demand. This became one of the foundational pillars of the petrodollar system. But the structure of the global economy is beginning to evolve. Energy itself is diversifying. The world is gradually moving toward nuclear, renewables, solar, battery systems, localized grids, and diversified energy architectures. Oil remains important, but it is no longer the uncontested singular backbone of industrial civilization. At the same time, a new recurring global demand layer is emerging: AI compute. And unlike oil, AI compute possesses several unique characteristics: digitally meterable, globally routable, infinitely composable, machine consumable, and programmable at software speed. This matters because AI infrastructure may become one of the largest recurring utility layers ever created, not merely for humans, but for machines. That distinction changes the scale of demand entirely. Human economic activity is constrained biologically. Machine economic activity is not. Autonomous agents can transact continuously, optimize continuously, route continuously, and consume compute continuously. The economic implications are enormous because once AI agents, robotic systems, autonomous logistics, machine research, and synthetic labor networks all begin operating simultaneously, civilization creates an entirely new category of perpetual infrastructure demand. Inference becomes continuous industrial consumption. This is where stablecoins become critically important. Stablecoins increasingly function as machine-native settlement rails, programmable accounting systems, and globally routable liquidity layers. Machines require stable units, low-friction settlement, sub-cent precision, and predictable accounting. Stablecoins satisfy those conditions extremely well. This is one reason stablecoin growth has accelerated so rapidly. The stablecoin market has already expanded into the hundreds of billions of dollars, with annual transaction volumes reaching into the tens of trillions. Meanwhile, issuers such as Tether and Circle have become major holders of short-duration U.S. treasuries. Tether alone accumulated well over $100 billion in treasury exposure through direct holdings and repo arrangements. This creates an important monetary loop. AI compute demand drives stablecoin usage. Stablecoin growth drives treasury demand. Treasury demand reinforces dollar liquidity and global monetary reach. This is why the AI economy may not necessarily weaken dollar dominance. It may extend it. The implications become even more important once machine-to-machine settlement scales globally. Historically, the petrodollar system recycled global energy demand back into dollar reserves, treasury markets, and U.S. financial infrastructure. The emerging AI economy may create a similar dynamic around compute, inference, machine commerce, and tokenized infrastructure. This is why the phrase, "compute becomes the new oil," is more than a metaphor. It describes a possible monetary transition, one where AI infrastructure demand becomes a structural source of recurring dollar demand. Especially if dollar-backed stablecoins dominate machine settlement, protocol infrastructure remains globally accessible, and the United States maintains leadership across chips, AI models, cloud infrastructure, and financial rails. This is where geopolitics enters the picture, because AI stacks are increasingly becoming monetary stacks. The U.S.-aligned ecosystem currently possesses several advantages: advanced semiconductor leadership, hyperscaler dominance, open AI ecosystems, deep capital markets, and globally liquid dollar stablecoins. Meanwhile, China is constructing a parallel architecture around sovereign infrastructure, domestic AI ecosystems, ECNY, and controlled payment rails. Europe explores digital Eurosystems, sovereign AI initiatives, and strategic autonomy. Other nations increasingly face a strategic choice. Which AI stack do they integrate into? Because choosing an AI stack may increasingly imply choosing payment rails, settlement systems, infrastructure standards, and monetary ecosystems simultaneously. This is what makes AI infrastructure potentially stickier than oil infrastructure. Oil is geographically distributed and relatively fungible. AI ecosystems are not. AI stacks accumulate data, models, developers, infrastructure dependencies, payment integrations, and machine behavior patterns. Once agents, enterprises, robotic systems, and infrastructure providers standardize around a stack, switching costs become enormous. That creates deep network effects, and those network effects may extend directly into monetary systems. This is one reason stablecoins may become strategically important beyond crypto speculation. Stablecoins increasingly resemble the transactional lubricant for machine civilization, not merely because they are digital dollars, but because they are programmable, globally routable, machine compatible, and deeply interoperable with tokenized infrastructure systems. At the same time, protocol tokens continue solving ownership, staking, governance, and decentralized coordination. Together, stablecoins and protocol tokens create a hybrid monetary architecture: stablecoins for settlement, protocol tokens for infrastructure coordination. This distinction is crucial because without the coordination layer, the AI economy remains centralized, and without the settlement layer, machine commerce struggles to scale globally. The emerging system increasingly resembles a globally programmable utility economy, one where compute is metered, machine labor is rented, infrastructure is tokenized, settlement is automated, and ownership itself becomes programmable. This may ultimately represent a major evolution in the structure of global capitalism itself. Not the end of markets, but the expansion of markets into machine capability, machine coordination, and programmable infrastructure. And that transformation points toward a much larger civilizational shift: the transition from attention extraction to metered civilization. Section 8, Conclusion: From Attention Extraction to Metered Civilization. For most of the internet era, the dominant business model of the digital economy revolved around one idea: capture human attention. Platforms competed for clicks, engagement, watch time, emotional reactions, and behavioral manipulation. The infrastructure layer itself remained largely invisible to users because the economics were subsidized through advertising and data extraction. But the rise of agentic AI changes the consumer at the center of the system. Machines become the primary users of compute, inference, storage, APIs, robotic services, and machine coordination systems. And machines fundamentally change the economics of the internet. Machines do not click advertisements. Machines optimize for utility, speed, reliability, and cost. This shifts the architecture of the global economy away from attention extraction and toward metered infrastructure. That distinction may ultimately define the next phase of civilization. Because once intelligence becomes measurable, programmable, allocatable, and economically routable, machine capability itself becomes a commodity, a utility, and eventually a financial asset. This is the deeper pattern underlying the convergence of AI, crypto, stablecoins, tokenization, robotics, and decentralized infrastructure. The world is not merely building better software. It is constructing a new utility layer for civilization. And like every major utility before it, electricity, telecoms, cloud computing, transportation, and industrial energy systems, AI infrastructure requires pricing systems, settlement rails, ownership structures, coordination mechanisms, and globally scalable capital formation. This is why tokenization becomes so important. Tokenization transforms machine capability into programmable ownership, rentable infrastructure, yield-bearing assets, and globally tradable economic primitives. Stablecoins increasingly function as the payment rails of machine commerce. Protocol tokens increasingly function as the coordination and ownership rails of machine infrastructure. Together, they create the foundational architecture for a metered, programmable, machine-native economy. This is already visible across decentralized compute protocols, AI infrastructure markets, staking systems, GPU marketplaces, robotic automation, and machine settlement networks. The implications extend far beyond finance, because once compute and synthetic labor become tokenized, rentable, and globally coordinated, the distinction between capital, infrastructure, and labor begins to blur. Machine capability itself becomes financialized. That may ultimately become one of the defining economic transitions of the 21st century, not simply the rise of AI, but the rise of programmable machine civilization, a civilization where compute behaves like industrial fuel, machine labor behaves like infrastructure, robotic output behaves like rentable capital, and settlement occurs autonomously between machines. This is why decentralized coordination layers matter. Without tokenization and protocol infrastructure, the future machine economy risks becoming extremely centralized. A handful of hyperscalers could own the compute, the robots, the inference systems, the settlement layers, and the productive machine economy itself. But tokenized infrastructure introduces another possibility: distributed machine ownership, where individuals globally can participate in infrastructure, own portions of machine capability, stake into productive systems, receive yield from automation, and collectively coordinate global machine infrastructure. This is one reason the convergence between AI, stablecoins, protocol tokens, and decentralized infrastructure may become historically significant. Not because crypto replaces governments, not because AI magically eliminates scarcity, but because programmable infrastructure fundamentally changes how civilization coordinates ownership, production, labor, and economic participation. The world is moving toward a metered, tokenized, agent-native economy where compute becomes the new oil, protocol tokens become the plumbing, and stablecoins become the lubricant.